Hi everyone. In this video, we are going to learn about gases and the ideal gas law. Let's start by just thinking about different types of gases. For example, do you know what gases are in air? Well, air is made up of about 78% nitrogen gas, about 21% oxygen gas, about 1% argon, and then a little bit of carbon dioxide, methane gas, ozone, and hydrogen gas. And now the reason I'm talking about air is because it shows that gases are all around us. But what is the definition of a gas? Well, a gas is a substance in a gaseous state of matter. Because gas is just one of the four natural states of matter. It's right there with the solids, the liquids, and the plasmas. And now what differentiates a gas from the other states of matter is that a gas has no fixed shape or volume. And now that we've got a general understanding of what it means to be a gas, let's look at the basic properties of gases. We are going to look at four basic properties of gases. These properties are pressure, volume, temperature, and amount, where the amount refers to the number of moles of gas. Let's take a quick look at each of these properties. Pressure can be defined as the force per unit area. When gases are in some sort of container, or in this example, in a balloon, they're moving all over the place. And so that means they're going to collide with the walls of the container. And during these collisions, the gas particles apply a force to the walls of the container. This force is applied over a certain area, and that produces pressure. And now when it comes to the units of pressure, there are many different units that you might come across. Pressure can be measured in atmospheres, pascals, kilopascals, milligrams of mercury, bars. So make sure you know how to convert between the different pressure units. Here's a little conversion table to help you. The next property is volume. Volume just describes how much space the gas takes up. So maybe the gas is stored in a 1 liter container or it's stored in a 10 liter container. The next property is temperature. Temperature just describes how hot or cold something is. But you have to be careful, because when we're dealing with gases and the ideal gas law, temperature must always have the units of kelvins. So a lot of the times you will get temperature in Celsius, and you need to remember to convert it to kelvins. How do you do that conversion? Well, if you want your temperature in kelvins, all you need to do is take your temperature in degrees Celsius and add 273.15 to it. Now let's look at the last basic property, which is amount. This refers to the number of moles of gas. How do you calculate the number of moles? Well, we can use this equation, which says that the number of moles of gas is equal to the mass of the gas divided by the gas's molecular weight. So those are our four basic properties of gases. And now we're going to look at Boyle's law, Charles' law, and Avogadro's law. These three laws helped build the ideal gas law. Let's start with Boyle's law. The equation you need for Boyle's law is P1V1 is equal to P2V2. When Boyle's law was being derived, what the chemists did is they took a gas and they held its temperature constant. They also kept the amount of moles constant. The only variables they changed were pressure and volume, because they wanted to see the relationship between the pressure and volume. And what they found is that pressure and volume are inversely proportional. Now, what does that mean? Well, it means if the volume of a gas decreases, then the pressure will increase. On the other hand, if the volume increases, what's going to happen to the pressure? Well, the pressure is going to decrease because pressure and volume are inversely proportional. So when one of them increases, the other decreases. And a lot of you might have experienced this in real life. If you get a bag of chips at the airport and then you bring it on the airplane, you might have noticed that when you're in the airplane, the bag of chips has expanded. Why does this happen? Well, the bag of chips has gas in it, and when you go up into the airplane, the pressure around you is lower. Lower pressure means the gas will have a higher volume. That's why the chip bag expands. So when it comes to Boyle's law, remember, pressure and volume are inversely proportional. Now let's do a quick example to practice using this equation. Here we have a sample of gas which has an initial volume of 5.8 liters and is at a pressure of 0.85 atmospheres. If the volume is increased to 10 liters, we want to know what will the pressure be. Well, all we need to do is use our P1V1 is equal to P2V2 equation. We can rearrange for P2, then plug in our values, and when we do the math, we find that the pressure would have decreased to 0.49 atmospheres. And now, does this answer make sense? Since the volume increased, we would expect the pressure to decrease. So yes, this answer makes sense. Now let's explore Charles's law. The equation you'll need is V1 divided by T1 is equal to V2 divided by T2. But what does this mean? Well, in this experiment, they held the pressure of the gas and the amount of moles of gas constant, and then they changed the volume and temperature to see what the relationship would be. And what they found is that volume and temperature are directly proportional. Now, what does this look like? Well, as the temperature increases, the volume increases. As the temperature decreases, what do you think will happen to the volume? It's going to decrease as well. When you increase one, the other increases. When you decrease one, the other decreases. And a classic example of this is when you take a balloon and you fill it with a gas. Then you take that balloon and you put it in some liquid nitrogen. And liquid nitrogen is really cold. It can get to negative 196 degrees Celsius. So what do you think happens to the balloon when you put the balloon in liquid nitrogen? Well, it shrivels up. So it decreases in volume because the temperature decreased. So what you need to remember for Charles' law is that volume and temperature are directly proportional. Now let's jump right into an example to practice using this equation. In this question, we have a gas that's stored in a balloon. At some unknown temperature, the volume of the balloon is 3 liters. But when the temperature is decreased to 0 degrees Celsius, the volume of the balloon drops to 2.5 liters. And based on this, we want to determine the original temperature. Now all we need to do is use our V1 divided by T1 is equal to V2 divided by T2 equation. Then we just need to rearrange for T1. Now before we plug in our values, make sure that you've converted the temperature to kelvins. To do this, all you need to do is take the temperature in degrees Celsius and add 273.15. So when the temperature is 0 degrees Celsius, it would be 273.15 kelvins. And now we have everything we need to plug our values into our equation and solve. And what we find is that the original temperature was 328 kelvins. And now I know it doesn't say to convert to degrees Celsius, but let's do it just for practice. All we need to do to convert from kelvins to degrees Celsius is take our temperature in kelvins and subtract 273.15. When we do that, we see that the original temperature was 55 degrees Celsius. Now let's look at Avogadro's law, which says V1 divided by N1 is equal to V2 divided by N2. Now in these experiments, they held the temperature of the gas and the pressure of the gas constant, and they varied the volume of the gas and the amount of moles of gas. And what they found is that the volume and amount are directly proportional. What does that mean? Well, as the amount of gas increases, the volume increases. And when the amount of gas decreases, what happens to the volume? It decreases. And at least to me, this just makes sense. If you have less moles of gas, they take up less space. Versus if you have more moles of gas, they take up more space. So Avogadro's law is pretty straightforward. You just have to remember that volume and amount of gas are directly proportional. Let's do a question to practice using this equation. Here we have 0.23 moles of helium gas, which has a volume of 5 liters. If the number of moles was increased to 0.35, what would be the volume of the gas? This is a very simple question. All we need to do is use our V1 over N1 is equal to V2 over N2 equation, rearrange for V2, and then plug in our values. When we do the math, we see that the volume would increase to 7.6 liters. And this makes sense because amount and volume are directly proportional. So because the moles increased, the volume should increase as well. And now it's time to look at the ideal gas law. Check out my other video on how the ideal gas law was derived if you're curious about how Boyle's law, Charles' law, and Avogadro's law were all used to derive the ideal gas law. But really, all you need to know is that the ideal gas law is PV is equal to nRT. And now the reason it's called the ideal gas law is because technically it only applies to ideal gases. And now ideal gases are hypothetical. They don't exist in real life. But the ideal gas law still provides a good model and helps us predict the behaviors of real gases. So now let's take a look. P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the temperature. And now you can represent the gas constant in a variety of units, but I will be using this value of R, where R is equal to 8.3145, and the units are liters, kilopascals, per mole per Kelvin. You should use whatever R value your teacher recommends. And truly, it doesn't matter because no matter what R value you use, you should get the same answer, as long as you make sure that your pressure, volume, and temperature are in the correct units. So for the R value that I will be using, the pressure needs to be in kilopascals, the volume needs to be in liters, and the temperature needs to be in kelvins. You can look at the units of the gas constant to figure out what the units of pressure, volume, and temperature need to be. And now let's jump into a few examples to practice using the ideal gas law. Alright, we're going to do 2 practice questions using the ideal gas law. This one's the first one, and it's pretty simple. We want to know how many moles of gas are in a 3.5 liter basketball that has been inflated to a pressure of 1.68 bar at 25 degrees Celsius. The first thing you want to do is write your ideal gas law. Then we can rearrange and isolate for the number of moles. Now before you go plugging in any values, you need to make sure everything has the correct units. Now if I use this gas constant, the pressure has to be in kilopascals and the temperature has to be in kelvins. So let's start by converting our pressure into the correct units. We know there's 100 kilopascals in 1 bar. So when we do the conversion, we can see that the pressure is 168 kilopascals. Now let's convert the temperature from degrees Celsius to kelvins. To do this, all we have to do is 25 degrees Celsius plus 273.15. And that gets us 298.15 kelvins. And now we have everything we need to solve for the number of moles. All we have to do is plug in our values. And then when we do the math, we can see that the number of moles of gas is about 0.24. So that's how you use the ideal gas law. But honestly, this was a really easy question. Let's try a more challenging problem. Now in this question, we're working with this chemical equation, which says that carbon monoxide and hydrogen can combine to form methanol. We want to know what volume of hydrogen gas at a pressure of 1 bar and a temperature of 86 degrees Celsius is required to synthesize 25.8 grams of methanol. So if you're confused as to where to even start with this question, just write out your equation. We have pressure, temperature, volume. That indicates we should use the ideal gas law. We want to solve for the volume, so let's rearrange for V. Now we know the gas constant R, we know the temperature, and we know the pressure. That means all we need to solve for the volume is the number of moles of hydrogen gas. How do we find the number of moles of hydrogen gas? Well, let's look at our chemical equation. We need to find the relationship between hydrogen and methanol, and we can do that by setting up a molar ratio. So I write the number of moles of hydrogen over the number of moles of methanol is equal to 2/1. The 2 is from the coefficient in front of hydrogen. The 1 is from the coefficient in front of methanol. And when we rearrange this to isolate for the number of moles of hydrogen, we can see that the number of moles of hydrogen is equal to 2 times the number of moles of methanol. Now this tells us that we need to find the number of moles of methanol. How do we do that? Well, this is the equation for the number of moles. We know the mass of methanol is 25.8 grams, and we can calculate methanol's molecular weight, which would be 32 grams per mole, and we find that the number of moles of methanol is about 0.806. And now we can solve for the number of moles of hydrogen gas. It would just be 2 times the number of moles of methanol. So we find that the number of moles of hydrogen gas is about 1.61. And now we almost have everything we need to answer this question. But before we use our ideal gas law equation, we have to make sure everything is in the correct units. So we need to convert our pressure into kilopascals and our temperature into kelvins. And now we have everything we need to solve for the volume of hydrogen gas. We just have to use the ideal gas law and then plug in our values. And what we find is that the volume of hydrogen gas is about 48.1 liters. And that's the end of this more complicated example of how you can use the ideal gas law. Now the last 2 topics that we're going to discuss are applications of the ideal gas law. So the first one is molar volume at STP. First, I'll just give you the definition. Under STP, which is standard temperature and pressure conditions, 1 mole of any ideal gas occupies the same volume, and that volume is 22.7 liters. Now I've seen examples where the molar volume at STP is 22.4 liters. If this is the number you were taught, that means your STP conditions use pressure in atmospheres. I was taught that STP conditions have pressure in bar, so that's what we're going to be using, and that means the molar volume at STP is 22.7 liters. But let's break this down. First off, when you see STP, that stands for standard temperature and pressure. This is a set of conditions where the temperature is 0 degrees Celsius, so 273 kelvins, and the pressure is 1 bar. And now what we're saying is that if you're in these STP conditions and you have 1 mole of gas, the volume of that gas will always be 22.7 liters, no matter what type of gas it is. And I challenge you to use the ideal gas law to prove if this is true. Now let's do a question to help us understand this. In this question, we're asked which sample of gas will have the largest volume at STP conditions. And now my challenge to you is to answer this question without using the ideal gas law. Because sure, you could use PV equals nRT, rearrange for V, you know the gas constant, you know the temperature and the pressure, because it's STP conditions, and all you would need to do is solve for the moles of all three gases. And then you could solve for the volume of hydrogen, oxygen, and argon. But that's too slow. Truly, you can answer this question without doing any calculations. Now, how did I know this? Well, at STP conditions, 1 mole of any ideal gas has a volume of 22.7 liters. So for example, if I had 1 mole of argon gas, it would have a volume of 22.7 liters. But what if I had 2 moles of oxygen gas? Well, its volume would be 2 times 22.7 liters. That gets us 45.4 liters. Now what if I had 3 moles of hydrogen gas? Well, its volume would be 3 times 22.7 liters. So it would have a volume of 68.1 liters. Now the reason I'm showing you this is because it proves that the gas with more moles has a larger volume. So all you need to do is figure out which gas has the most moles. Now how do we figure out the number of moles? Well, we know we can use this equation. But here's the catch. Every one of these gases has a mass of 1 gram. That means the only thing that's going to change the number of moles for each of these gases is their molecular weight. So the smaller the gas's molecular weight, the more moles that gas will have. So whichever gas has the smallest molecular weight will be the gas that has the largest number of moles, and that will be the gas that has the largest volume. So which of these gases has the smallest molecular weight? The answer is hydrogen. And that's why hydrogen will have the largest volume at STP conditions. And of course, I challenge you to use the ideal gas law to prove if hydrogen really would have the largest volume. The second application of the ideal gas law is that we can determine the density of a gas. And I'll just share the equation with you now. The density of an ideal gas is equal to Pm divided by RT, where m is the gas's molecular weight. Now this equation is actually pretty easy to derive, so let's do it together. We know that density is the mass of a substance divided by its volume, and it can have units of grams per liter. Now if we start with our ideal gas law, and then we rearrange it so that we have N divided by V is equal to P divided by RT. Looking at the N divided by V, N is the amount in moles, and V is the volume in liters. So we have units of moles per liter. Well, if we multiply moles per liter by grams per mole, which would just be the units from the gas's molecular weight, you can see that we get the units of grams per liter. So what that tells us is that if we multiply both sides of this equation by the molecular weight, we will have an equation for the density of the gas. And what we see is that D is equal to Pm divided by RT. And now let's jump right into a question to practice using this equation. In this question, we're asked to calculate the density of nitrogen gas at 125 degrees Celsius and a pressure of 750 milligrams of mercury. Now we just learned the density equation, so all we need to do is plug in the values for the pressure, the molecular weight, the gas constant R, and the temperature. Now before we plug these values into our density equation, remember that because I used this gas constant, the pressure needs to be in kilopascals and the temperature needs to be in kelvins. So let's quickly convert 750 milligrams of mercury to kilopascals. So that means our pressure is 100 kilopascals. And then when we convert our temperature from degrees Celsius to kelvins, we see that the temperature is 398.15 kelvins. And now we have everything we need to solve for the density of nitrogen gas. All we need to do is plug in our values, and then when we do the math, we can see that the density of nitrogen gas under these conditions is about 0.846 grams per liter. So that's how you calculate the density of ideal gases. And with that, that's the end of this lesson on gases and the ideal gas law. Thanks for listening, and good luck with your studying.